Hi, this is Larry. This is day 13 of the 30-day Leetcode challenge. Today let's take a look at the problem contiguous array. Hit the like button, hit the subscribe button, hit all the buttons, leave a comment. Let me know how you did on this problem. But I'm going to go right now. Contiguous array. Given a binary array, find the maximum length of a contiguous subarray with equal numbers of 0 and 1s. Okay. Uh, hmm. So length of array is 50,000. Um, so that's good to know. So the first thing that I would think about is kind of the complexity that I would think about in attacking this problem. Now that we know that n is 50,000, then you know that, well, n squared is probably out of the question. N log n maybe is okay. We'll see if we could figure it out. But obviously, if we could find a linear solution, that would be great. And one common technique that I'm going to use here is something called prefix sum. And what I'm going to create is an array that contains the sum from the index from 0 to the ith index. And that will allow us to calculate the sum between two indices. Um, and the reason why that's probably or possibly helpful here, this is just my thought, I haven't really solved this yet, um, is so that we can look up, because if we look up any two indexes, I and j, and so the length is I minus j plus 1, and if half of those, and if the sum is I minus j plus 1 over 2, then we have equal number of zeros and ones. So let's start that way, and then we can play around with, well, we could keep thinking about it afterwards. Um, enumerate. Okay. And now we have that. Now, how do we want to figure it out, right? What is the longest contiguous subarray? So I have a couple of ideas that I'm thinking about, and yeah, I'm gonna have to try to validate them. The first idea I had is a sort of a sliding window, or two fingers algorithm, or two pointers algorithm, um, and can keep on going. Hmm. Let's see, right? Um, I think I'm so, but with the algorithm, the two-finger algorithm with sliding window, the idea behind that, or the concept that I would try to use behind that to solve any problem in general, is that you have two fingers or two pointers. Everything inside there is some invariant that holds true, and no matter how you move your fingers left or right, at the end of the moving, that invariant still holds true. Uh, and I'm just thinking through whether we have anything like that here. Um, hmm. Yeah, I don't immediately have um, an answer. Uh, Sometimes you could do that with a proof that is greedy on something, so that because with the two fingers algorithm, you have to, whenever the invariant is not true anymore, there you need to kind of like nudge your fingers or pointers a little bit so that the invariant still holds true after the moving. Um, while while we can do something like that, um, I don't know if I don't know if we can. Because I don't have any greedy algorithms off my head that or that I can prove to myself that is true that would satisfy that, right? But another thought that I was thinking is some sort of binary search in some way, and there are a couple of dimensions that we could think about binary search. Um, the first one being that well, is there a good contiguous subarray of length n, or sorry, length k for some k. Um, I don't think that we can innately binary search on that because just because there's not a contiguous subarray of length, say, you know, 2, like for example, like in an extreme case, is that true? Hmm. Well, I guess the crappy example that I said was not true, but hmm. So I guess my question was, and I don't think that's true because you can have something like, um, is it? Hmm. Maybe it is. So what I wanted to say was, does the existence of like if n equals to 6 is true, does that mean n equals 4 is always true, or k equals 4 is always true for some k? Huh. I guess maybe. Hmm. I think my intuition said, didn't really, or like I feel like I would have to prove that, and my intuition is not leaning that way, but my intuition could be wrong, right? That's why we're thinking about it. Um, because it seems like playing around with that seems like that's what I am seeing. So that's what I think I'm gonna go with. Um, yeah, okay. Because why is this true? Because there's only really a couple of combinations. Um, maybe you can prove this because if there's because I was trying to think about whether there's a way such that you can have an n or a k equals 6, but no k equals 4. But I am having trouble constructing that because this here and then by symmetry, there's a lot of bisymmetry ones, and this one is one of the only other case as a result. So and then maybe you could do this inductively too as well. Is that we start with k equals 2. Um, there are only a couple of possibilities. So this is k equals 4, but another k equals 4 is just uh, literally the opposite. Which both contains k equals 2 as a start. Um, and then you could kind of maybe construct it that way. And if that's true, then you can binary search. Um, okay, maybe I am convinced now a little bit inductively. Um, it's a weak proof. It's not a mathematic proof, but I think it's good enough for me to start. So I'm going to start writing a binary search as a result. Um, I believe. So this is how I write my binary search in general. Then is equal to n. Use whichever binary search you're comfortable with. So I choose the one where f sub 0 is, and this is actually what we want is n over 2, right? Because we have to multiply it afterwards by 2 to get the double. And is that, and now I'm just thinking a little bit of like, given an odd number, is that okay? And it should be, because n divided by 2 times 2 should be the n minus 1, so that should be okay. And then now let's write the binary search. So yeah, what we say, middle is equal to left plus right divided by 2. You could also write this as left plus left plus what? What was it? Right minus left divided by 2. But I don't know. I mean, in Python, it's not as necessary. But okay, so if that's just like if good, or maybe a better name, if found of middle, then left is equal to middle plus 1, else right is equal to middle. And then now we just return left, right? And then now we have to write the found function. And then for some k, as we said. Okay, so now here we use the sliding window, as we said, to find. So given a length of k times 2, we want to find at least k1s and k0s. So let's kind of do that. And actually, it's not, now that we have given a specific length, it's not, I mean, it's a sliding window, but it's not a, it's just like checking between 0 and 0 plus k, and then 1 and 1 plus k, and so forth, which you'll see in code. And you could, because of this prefix sum array, we can do that actually in constant time. So everything is linear as a result. So as a result, this is n log n, which we'll go over in a little bit. Let me make sure this is right first. But okay. So for let's go ahead start index in range of from 0 to n. Let's just say 0 to n is probably like n minus k times 2. Do I have to add plus 1? As you go from 0 to k times 2, I always get all 5 ones on these, so I'm trying to be a little bit careful. But yeah, I think that's okay. But I think I have to add 1 to. I may be wrong on this one. I'll double check it later. But now we just have to check whether sums of the start plus k times 2 minus sum of start is equal to k. And if it is, then we return true. At the end, we return false. And then I think that's roughly it. That's one first case, and then also one the second case. But also maybe some other cases. Oops. I have to write this out a little bit. Okay. And also maybe empty arrays and stuff like this. Okay, so this is a little bit off, or a lot off. But I think also I searched on the k, so this maybe needs to be multiplied by 2, but there may be an off by 1 somewhere, so I have to kind of double check that. it should not be 4, for example, but actually, I think we could just do this. But one of the answers will be wrong. It should be 6 bit. How did we get 8? I think I did it backwards because 0 is always going to be true. So actually, my index is a little bit wrong. So let's do a 9, and then we reverse this. This isn't right? And we want the function to be force at 0. But I think I just did a double negative, so I don't think that fixes it. So we want, so I have to think about a little bit about how this, I historically have practiced or have not, this is good, and this should return true. Did I do this backwards? Off by one's always a little tricky. So we want it to be force from 0 to e. Should be right. So then this would be, no, I mean, I guess it's okay. It's just that, in this case, then we want left minus 1. Because then this would be the biggest one. But then, yeah, I think I need to be slightly more clear what I want. Binary search. Need to practice that a little bit. But I don't think this is right either. Yeah. Because then now it's not terminating. So I'm used to writing this in a very specific way where this would be not true. Be forced into because in this case it's just true from 0 to 3, and then we want 3. But instead, yeah, because it's true at 3, it returns 8. So it returns the first answer that's after this answer. Okay. How do we inverse the found? Okay, then I guess we could just do k is equal to n minus k times 2. That'll be the inverse. That is just awkward though. So now I need to debug this in a second. Hang on. One is true, so yeah, okay. That makes sense all the way through, and this is why, because it returns the one that's afterwards, the biggest, because we're the inverse of it. Yeah. This is one practice by research, but and then now to inverse it, because if we just inverse it, it still just gets the next one. That is, so it returns the 4, but we actually want this. Good enough. Really lost on this one. Basically, we just have to convert this function to from 0 to 2 is false. What I did was kind of on the right track, but I have to return the result in a reasonable way as a result. So that now returns a 1. Right? No. I have to debug this. But it is a good opportunity for me to learn, I suppose. Oh, right. Now we can do the not. Oops, that's why. Maybe, hopefully. Okay, I think this is right. Because now we just have to re-invert this, which is okay. This is a little bit of a mess to explain. I think I just need to also update how I think about binary search. Um, but okay, let's submit now then. Oof. Maybe my assumption is not right though. Let's see. Or the assumption that I can binary search. Um, let's debug this. Hmm. Man, I am struggling today. Okay, this one. It seems like I was wrong on the binary search because you could kind of see the gaps in these, which means there is, um, which is probably why it's returning the wrong answer. Uh, that's unfortunate that our assumption was wrong. So we have to think about another strategy then. I mean, I was struggling with the thing anyway. Let me think a little bit. So the question is, can we do the two-finger algorithm in another way? Uh, hmm. Spent way too long on binary search. That didn't work, but hmm. I think I have another thought about this. Uh, and I think the way that I would think about it maybe is uh, this actually now a little bit reminds me of that classic dynamic programming problem where sum equals to zero, or hmm, or trying to find yeah, I mean, it kind of reminds me a little bit of that target sum is 0, 0, where instead of 0 and negative 0 and plus ones, we have negative ones and plus ones. Then to cancel them out, you would get 0. And from that, you could kind of do a dynamic programming on that to calculate if there is a number that sums it to 0. What if, okay, I don't know if that makes sense. Uh, So maybe we don't need the prefix sum, but we do need a dynamic a hash table. So the current count goes 0, so the current sum maybe. Let's just do this by 1. L 1. And then now maybe we could do a lookup if count in H. We want count or negative count to sum to 0. Then and we want the first index, right? So maybe something like and the current would be index minus H negative count, and then that is maybe something like best is equal to max of best, something like that maybe. I'll play around this first. Well, clearly that didn't work out. But so you have negative 4. Well, we want this 1 to at least be well, then this would be negative 3. How would that match? Then it's negative 1, negative 2, negative 3, negative 4, and then this would bring it back to negative 3. So actually, then we don't want the negative count then, right? I always get confused on the sign on this, but okay. I mean, this is still wrong, but at least is this better? I don't know. This is negative 2, and negative 2 should match up with this one. But maybe I have an off by 1, but that still shouldn't matter. Alright, let's just put it off for debugging. Huh. Oh, I guess plus 1. So that doesn't seem like that would fix it, but at least it should count correctly at least. It's necessary, but it's not sufficient. Okay. So at index 4, 5, 6, 6 will return 2, even though it should return. Oh, oops. I actually was thinking about this when I was but I forgot. It should be an else, because if it's in there, then we don't want to update it. Just forgot about this because I was focusing on the other part. Okay. Now let's try again without the print statement. Okay, cool. Uh, there are definitely couple of a lot of things to say about this one. Definitely, I think well, one is to be an interview. Definitely don't give up. You have 45 minutes to an hour, and in this case, use about 35 minutes. Sometimes it happens, you struggle, and that's okay. But as long as you keep on, as long as you kind of keep on working at it on it, because sometimes your assumptions are wrong, and clearly my assumption was wrong. I was trying to I think I was, as you kind of saw, I was trying to attack it with binary search. I was very full about it. I kind of came up with some stuff, but clearly, apparently, it's not wrong. There was a count, or sorry, it's not correct. There was a counter case, which I should dig into a little bit because I thought, I mean, I proved it. I don't want to say prove it, but I convinced myself with small cases and it seemed okay, but it was still wrong, right, at the end of the day. Um, I think prefix sum. I mean, this is actually an interesting application of that dynamic programming thing. Um, was there a couple of ways to go about it, and I still was trying to think about whether the two finger algorithm worked, but but yeah, in the end, it was dynamic programming. It is a classic. Uh, it's one of the classic dynamic programming problems, though. At least this one, it's not. Maybe it is, but it's not something that I am well practiced in. And also, I just struggle with binary search in general, so maybe I should work on that. That would save some time for sure. Um, and the code ended up being really short. Um, but yeah, so the idea behind this code is that so I keep a running count of all. Or basically, this is actually um, essentially what we did earlier with the prefix sum. It is just a prefix sum of where zero, we changed the we changed the zero to a -1, so that I so that uh, it gives us the ability to count, so that you know that they sum to zero, and you know that to look for zero, and the thing here is that when you get a target 0, 0, then you know that the number of zeros and ones are equal. Um, but knowing that, you're trying to get the length, right? And that's kind of what I did here with keeping track of the length. Actually, this reminds me recently, I feel like I did a recent variation of this on a contest somewhere, um, but clearly not practice enough for this variation. I went down the wrong path, but that's okay. I would say uh, if you're in an interview and you get stuck, well, obviously you have to grind it through because why give up? You should not give up. You should not despair. You should kind of keep moving, keep on talking about your thought processes. I think if I went down that path on a real interview, the interviewer will likely be like, "Hey, are you sure about this binary search thing?" And then maybe save me some time, um, or maybe they let me struggle to be like, sometimes they will let you struggle for like 5, 10 minutes and then be like, oh, actually, you know, there's this case. Have you considered this case where it is not true? And this is something that I'll probably fill in a little bit. Um, but once I get past that, I'm able to do the dynamic programming part, which is, I guess, a little bit standard, but unfortunately, I took way too long on. But yeah, let's see. The code review. I mean, this is a like a 15-line code, so I wouldn't there's not much to clean up. I mean, you could change some of these things to a one-liner, but that doesn't make it more readable. It just makes it more cute. So I don't think that would do much. But to explain just a little bit, so the complexity is linear because every loop it just does all of one operations. The most expensive being possibly the insertion into a hash table, which is all one for purposes of a hash table. You could talk about hashing and hash collusion and stuff like this, but yeah, let's go over one. Um, yeah, that's all I really have for that part. Um, in terms of explaining this, basically we use the, given that we're looking for the sum equals to 0, um, we store in the hash table the earliest index that we see that sum is equal to 0, because then that allows us to get the maximal contiguous subarray for the answer, because given the current index, and then you just kind of choose the, if there are multiple of them, you choose the one the earliest for that reason. And that's kind of how I wrote the code. As an interviewer, these problems, I feel like these are always a little bit, um, I personally don't feel like I see that many dynamic programming problems, especially of this type of but I've heard from my colleagues that they've seen similar things, so I definitely would be a little bit prepared, though maybe a little bit um, like there easier dynamic program problems that I would recommend studying on first. But this one is for better or for worse. Maybe not this particular problem, but a variation of it where it's just, okay, given an array, find the longest contiguous sum where the target 0, 0 is a very common problem. So I would definitely think about it. As a competitive programmer, I have definitely seen these problems uh, very recently, and now I feel kind of bad not getting this immediately. And there are a lot of similar problems. I would definitely recommend going through them. And that's all I really have. Um, yeah, can I think that another way I'm thinking right now is like, well, can I have, can I have, could I have done this recursively? Uh, I suppose the answer is yes, but it would be a little bit weird. It would be a little bit forced. Um, yeah. So yeah, the H is a hash table that contains um, the one based index of the last time that sum is reached. Um, so so a length, just illustrating. So a length 0, we start with the base case of 0 because, and with the 0, which we could be -1, I guess, if you want to be 0 index, but that's why we keep it +1 on here. Um, and then you just kind of keep track of the previous sums that you have seen before and the earliest case that's the case, right? So let's say you have a prefix sum of 0, 1, 2, 3, 4, and then 3, 4, 3, 4, I don't know, 3, 2, 3, 4. So when you're up to here, uh, you know that um, you know that you look up to the previous 4. Well, this length of 4, I mean, there's 5 numbers, so there's 4 delta. Um, that it sums to 0 because, well, if you think about it, that it does a -1, -1, +1, +1. So to get to the same number, it has the same number of zeros and ones, which is the -1s and +1s. And then from that, you you can see that there are multiple 4s, and you want the earliest case that comes up. So that's how I would think about this element. And then in H, we store the earliest case where, so okay, now it's a 4. Let's store that in the earliest way possible. So yeah, so that's how I would think about it. Tricky problem. It is a very specific type of dynamic programming that I keep on coming across in competitive programming, but still probably need a little bit more practice, me personally. So yeah, but that's all I have for this problem. Thanks for watching. See y'all tomorrow, and hopefully it'll be more interesting. Bye bye.